What's up, guys? I'm going to go over this problem number 2 on discussion 9. This is a pretty simple Snell's law problem, but it kind of goes from air to water, then water to air twice, so it kind of makes it a little difficult. But let's go ahead and get started. So the first question is asking, well, let's go over the problem first. It says a light ray of 500 nanometers enters the water tank, so we can see it entering over here, with an angle of incidence as shown in the picture. That's a deceiving sentence. As shown in the picture might not be what you actually see. That might not be the angle of incidence. But anyways, what is the angle of incidence with which it leaves the tank? So the question mark, hint, hint, that one's actually an angle of incidence. And then it's saying water has a refraction index of 1.3. Okay, so the first step, solving a problem where you're changing mediums at certain angles is, and I hope most of you see that by now, is using Snell's law. N1 sine theta 1 equals N2 sine theta 2. But now the question is, what are our angles? And this is where most students make their mistakes. So let's first draw our normal lines. And speaking of normal lines, I've actually had quite a few students in office hours be confused. So apparently Professor Neiman always used horizontal surfaces, and so you guys always thought that the normal line is vertical to that surface, and that's true. It is vertical to that surface, but all surfaces aren't going to be horizontal, right? So in this case, we have a vertical surface, right, or a vertical interface between two mediums. So our normal line is always perpendicular, so it makes a right angle perpendicular to that surface. So in this case, this green dotted line is our normal line, and I'm just going to go ahead and draw in a normal line for the exiting interface. Part of it's already drawn, but here, I'll just go ahead and extend this. There we go, like that. Okay, so the first step is figuring out, what the relationship is here. I want to figure out this angle, so I need to get from here to here. And this is kind of how I've been explaining it to a lot of the students. This is probably the most, I guess, comedic way I can explain it. Snell's law over here, you do Snell's law here. So Snell's law, 8th grade math, Snell's law, okay? So those are the three things you gotta do. So the first thing, let's figure out what the incoming angle is. Many of you are tempted to put 20, but it's not 20 degrees. In this case, it should be 70 degrees, because we need to find the angle relative to the normal. So that's 70 degrees. We have our n of the air, which is n equals 1. So over here is n equals 1. And inside the water is n equals 1.3. And then we're trying to find this angle right here. Let's call this angle 2. Right? So this angle right there. So we can just solve for that. And let me actually solve for that right now. Sine theta 2 equals n1 over n2 times sine theta 1, do the arc sine and all that, dot, dot, dot. I'm going to let you guys do that just because it's going to be a waste of time to calculate that. So what you end up getting here is you should get 46.2 degrees and equals theta 2. So this part right here should be 46.2 degrees. So let me see if I can write that in there really, really small. This should be 46.2. And again, now this is another part where students get pretty confused because they're tempted to maybe use this angle when trying to calculate this angle, but you can't do that yet. You need to find this angle over here. Let's call that theta 3. And to do that, we have to recognize that we have a right triangle right here. Right here, the right triangle. So 90 degrees here. So if the whole thing's 180, that's 46.2. Theta 3 has to equal 43.8, I believe. Yeah, 43.8. And then again, remember how I said Snell's law? We already did that. Basic geometry, we just did that. And then Snell's law again. So now we got to do N2, right? So 1.3. N2 sine 43.8 equals N1, the outside air, because we're, the 43.8 degrees here is respective to the n equals 2, or I mean n2, so 1.3. And then the exiting angle is respective to the outside end, which is 1. So times sine of question mark, right? So theta 4, whatever you want to call that. angle right there. So again, you guys can solve that. Angle equals what? That angle is going to equal 64.1 degrees. Your solutions might actually have it wrong, because I just realized whenever I was doing it, I used n equals 1.2 instead of 1.3. But I don't really care how you guys, what the actual numbers are. The point is that you guys understand how to do this problem, okay? So this should be your exiting angle, 64.1 degrees. So that's the answer to part A. So let's go ahead and move on to part B. Now it's asking, what does the original incidence angle? I'm actually going to go ahead and erase all this just because we don't need it anymore. Now here's where it gets a little bit tricky, right? Because we need to find the angle at which it comes in, so the angle that it comes in, such that this refraction never actually ends up happening. Because it's asking for, what does the original incidence angle have to be, this angle in red, for the light to reflect internally inside the water tank. So this has to come in at such an angle so that when it refracts, at this point right here, it refracts, it actually gets totally internally reflected, okay? So we need to figure out that angle. Okay, so we need to figure out the angle such that, let me write Snell's law equation.
Equals n2 sine theta 2.
So in this case, okay, I'm actually going to derive the critical angle formula just because I personally don't remember it. All I know is there's some angle over here that has to come in such that the exiting angle ends up being 90 degrees. Okay, that's the definition of total internal reflection. Okay, so this angle is going to be 90 degrees. Okay, so I went ahead and fast forwarded to writing the equation down for the theta critical. So we have our two n values, and we can find our theta critical. So n2 in this case is going to be which one? This is where you have to be careful that you orient yourself correctly. N2 is going to be the outside air in this case, because we're trying to find this angle, right? This angle. So the N2 is going to be the outside air, and the N1 is going to be the water on the inside. So that angle should give you theta critical should give you 50.3 degrees for this angle right here. 50.3. But again, let's make sure we orient ourselves. So if that's 50.3, I need to now find this angle, which is just going to be 90 minus 50.3, which would be 39.7. Yes, 39.7. And then again, we can just go back to basic Snell's law. So we can do N1, by the way, this 1 and this 2 are totally up to you as long as you orient yourself correctly. In this case, N1 is going to be the inside of the water. So N1 sine of 39.7 equals N2 sine of theta. Okay, and theta is going to equal theta 2 is going to equal 83 degrees, which makes perfect sense. Because if you think about it, the angle at which it comes in has to be steep enough to where when it refracts, it goes at a really, really steep angle, and that steep, large angle is gonna be what causes the total internal reflection. Remember how total internal reflection has to come when you have very, very shallow or very, near horizontal angles, and having a steep angle from the lower end medium is going to give you that shallow angle. If you play with the equations and mess around with the variables, you'll see why that's true. But this number shouldn't be too surprising, okay? So the answer for part B should be 83.0 degrees. Okay, that should be your incidence angle. And make sure that you know that it's that angle, okay? Not this one. It's that angle, 83.0. Okay, cool. Thanks for watching, guys, and good luck on finals.